Hello friends, welcome back to my channel Path of Physics. In this video we are going to discuss about cylindrical flow of heat. Using this method we find the equation of thermal conductivity of a cylindrical tube. So for that consider a cylindrical tube of length L, inner radius R1 and outer radius R2 as shown in the figure. I have drawn here the figure. See, this is the inner cylinder. Its radius is R1, and this is the outer cylinder. Its radius is R2. The tube carries steam or some hot liquid. The inner cylinder carries some steam or hot liquid. So heat is conducted radially across the walls of the tube. So after some time, steady state is reached. The temperature of inner surface is the inner cylinder is theta 1 and on the outer cylinder it is theta 2. See, the temperature of the inner cylinder is theta 1 and on the outer cylinder it is theta 2 after reaching the steady state. Means after steady state means after some time, after heating for some time, the temperature remains constant. It does not change with time. So at this state, we can say that our specimen has reached in steady state condition. Then the thick tube is imagined to consist of large number of coaxial cylinders of increasing radius. So among those coaxial cylinders, we select one cylinder of thickness dr, which is at a distance r from the axis of the tube. So here I have drawn one coaxial cylinder. Its thickness is dr. Its distance from the axis is r. Um, Now we have to find amount of heat flowing per second through the selected cylinder. It is given by the law of conduction. Q is equal to Ka times theta minus theta plus d theta by dr times T, where theta and theta plus d theta are the inner and outer surface temperatures of our selected cylinder. See, theta is the inner surface temperature of our coaxial cylinder and theta plus d theta is its outer surface temperature. And theta minus theta plus d theta by dr is a temperature gradient across our coaxial cylinder. Then K is its thermal conductivity of our tube. Then A is the area of the coaxial cylinder, curved surface area of the coaxial cylinder. T is the time, and we need to find the quantity of heat flowing per second through the selected cylinder. So here T is equal to 1 second. So on simplifying this equation, we get Q is equal to Ka times minus d theta by dr. On rearranging this, we get Q is equal to minus Ka times d theta by dr. Now we are going to substitute the value of A. A is the curved surface area of our selected cylinder. Its value is 2 pi RL. So on substituting that value, we get Q is equal to minus 2 pi RL times K times d theta by dr. Now remember one point, after reaching steady state, the amount of heat flowing through all the coaxial imaginary cylinders is same. It's same. If we imagine two coaxial cylinders, the heat flowing through both the coaxial cylinders will be the same at the steady state. So the number doesn't matter. After steady state is reached, the amount of heat flowing through all coaxial imaginary cylinders is same. Now on rearranging this equation, we get this equation. We get dr by r is equal to minus 2 pi L times K by Q times d theta. Now on next step we are integrating them. We are integrating both sides. So we get integral r1 to r2 dr by r is equal to integral theta 1 to theta 2 minus 2 pi L K by Q times d theta. Now this is of the form integral dx by x. Integral dx by x is log to the base e x. So this can be written as log to the base e r within the limits r1 to r2. And here in this RHS we take out all the constants, and it becomes integral d theta. Integral d theta is theta within see theta within the limits theta 1 to theta 2. We have reached this equation. Now in the next step we are going to put the limits. So we get log to the base e r2 minus r1 is equal to 2 pi L k by q times theta 1 minus theta 2. Now this LHS is of the form log to the base e a minus log to the base e b is equal to log to the base e a by b. So this can be written as log to the base e r2 by r1. And here we can write it like that itself, 2 pi L k by q into theta 1 minus theta 2. Now keeping k on the LHS and bringing other terms on the RHS, we get k is equal to q times log to the base e r2 by r1 by 2 pi L into theta 1 minus theta 2. This is our required equation for the thermal conductivity. This is a thermal conductivity of the tube, of the cylindrical tube we have taken. Now remember one more point. In this method, heat flows from inner tube, inner cylinder towards the outer cylinder along the radius of the cylindrical shell. So this is an example of radial flow of heat. So that's all for today. If there are any clarifications, please comment. Thank you.